Hello everyone, this is Aravind from the research domain of ACM. I am here to give an introduction to machine learning. For the people who wanted to start their ML journey, this might give them a quick glimpse of it. Before we go into ML, let us first know the history of it. In 1950, Alan Turing creates the Turing test to determine if a computer has real intelligence or not. To pass the test, a computer must be able to fool a human into believing it is also a human. And then later, it was 1952 when Arthur Samuel wrote the first computer learning program. The program was the game of checkers, and the IBM computer improved at the game the more it played, studying which moves made up winning strategies and incorporating those moves into its program. It is also to be noted that this was the first AI program to run, and Arthur Samuel is credited for coining the term machine learning. Wait, first of all, what is machine learning? Machine learning is a subset of artificial intelligence where computer algorithms are used to autonomously learn from data and information. The forte of machine learning computers is that they don't have to be explicitly programmed, but can change and improve their algorithms by themselves. A machine learning system learns from historical data, builds the prediction models, and whenever it receives new data, it predicts the output for it. These are some trends in machine learning, from the first neural network, the perceptron, to Google's AlphaGo algorithm developed by Google DeepMind, which defeated a professional player at the Chinese board game Go, which is considered the world's most complex board game and is many times harder than chess. The elaboration of each milestone would require a session of its own. Let's save it for another day. Now, let's jump into classifying ML based on how it works. At a broader level, machine learning can be classified into three types: supervised learning, unsupervised learning, and reinforcement learning. In supervised learning, the system develops a predictive model based on both input and output data. The other one, which is unsupervised learning. In this, the system groups and interprets the data based only on input data. The third one is reinforcement learning. It is a ML training method based on rewarding desired behaviors and punishing the undesired ones. Now let us see how a supervised learning model works. In supervised learning, the models are trained using labeled dataset, where the model learns about each type of data. Once the training process is completed, the model is tested on the basis of the test set. The test set is a subset of the training set, and then it predicts the output. The working of supervised learning can be easily understood by the given example and diagram. Suppose we have a dataset of different types of shapes, which includes square, rectangle, triangle, and in general, let it be a dataset of polygons. Now the first step is that we need to train the model for each shape. If the given shape has 4 sides and all of them are equal, then it will be labeled as a square. Likewise, if the number of sides is 3, then it will be labeled as a triangle. Similarly, other polygons will be labeled. Now, after training, we test our model using the test set, and the task of the model is to identify the shape. As our model is already trained on all types of shapes, and when it finds a new shape, it classifies the shape on the basis of the sides, and then it predicts the output. The overall aim of a supervised learning algorithm is to find a mapping function to map the input variable with the output variable. The next one which we are going to look into is unsupervised learning. As the name suggests, unsupervised learning is a machine learning technique in which the models are not only in which the models are not supervised using the training dataset. Instead, the model itself finds the hidden patterns and insights from the given data. It can be compared to learning which takes place in the human brain while learning new things. Let us understand unsupervised learning using a simple example. Suppose the unsupervised learning algorithm is given an input dataset containing images of different types of cats and dogs. The algorithm here is never trained upon the given dataset, which means it does not have any idea about the features of the dataset. The unsupervised learning algorithm will perform this task by clustering the images into groups according to the similarities between the images. In this way, an unsupervised learning algorithm can classify the raw input data, which is unlabeled, into classified outputs, which includes here we have cats and dogs in the unlabeled data, and in the output it classifies the images into two classes, that is cats and dogs. The next one that we are going to see is reinforcement learning. Reinforcement learning is a type of learning methodology in ML along with supervised and unsupervised learning. But when we compare these three, reinforcement learning is a bit different from the other two. Here we take the concept of giving rewards for every positive result and make that the base of our algorithm. Unlike supervised and unsupervised learning, reinforcement learning has a feedback type of algorithm. In other words, for every result obtained, the algorithm gives feedback to the model under training. For an easier explanation, let's take the example of a dog. We train our dog to perform certain actions. Of course, it won't be an easy task. We would order the dog to do certain actions, and for every proper execution, we would give a biscuit as a reward. The dog will remember that if it does a certain action, it would get biscuits. This way, it will follow the instructions properly next time. In a similar manner, a reinforcement learning agent is able to perceive and interpret its environment, take actions, and learn through trial and error. We have seen supervised learning previously, and it is classified into two. It is classified into regression and classification. Regression algorithms are used if there is a relationship between the input variable and the output variable. More specifically, regression analysis helps us to understand how the value of the dependent variable is changing to an independent variable when the other independent variables are held fixed. On the other hand, if we come to classification, classification algorithms are used when the output variable is categorical. In other words, it is used to identify the category of new observations on the basis of training data. In classification, a program learns from the given dataset or observations and then classifies new observations on the number of into a number of classes or groups. With this, I conclude my presentation of giving an introduction to machine learning. Thank you.
Alright, so we will start off with the classification examples. Over here, I have used a dataset which tells us whether a person has heart disease or not, and we'll be applying several classification algorithms to find out if the person has heart disease or not. So we'll start off by importing a few necessary packages. NumPy stands for numerical Python. This package helps us to do a lot of mathematical calculations. Pandas helps us with data analysis. Matplotlib and Seaborn are used to craft the data for better visualization. Okay, let's just run these cells. Alright, I'll tell you about smooth a bit later. These are the techniques that we'll be needing for calculating the accuracy and display certain graphs. These are the classification techniques that we'll be using for our dataset. We have logistic regression, decision tree, random forest, naive Bayes algorithm, SGD classifier, and XGB. Alright. Moving on, let's just import the data and let's have a look at what the data looks like. Alright. So these are the columns, as you can see: BMI, smoking, stroke, physical health, race, diabetic, physical activity, and at the end, if the person has skin cancer or not. You see, through df.info, we'll find out which values, like which columns has got null values and the count of null values. And all the D type, if you can notice over here, a few of them are objects and few of them are float. Now just note the object data types, because quite a lot of them are actually qualitative values and are not specified by number. So we'll have to work on them in order to make the dataset work. Over here, we'll be checking the different categories. You see, we are finding out which values are qualitative, and we are doing so by checking if the D type is object or not. Yeah, so in our dataset, these are the qualitative values, but among a few of them, there are actually quantitative values as well, but it's given in a range, like the age category. So just make a note of all these as of now. Yes. So over here, what we'll be doing is that we'll be separating the values into three forms: label, one hot, and quant. Now, label are gonna be those values on which we are gonna apply label encoding. One hot are gonna be those values on which we are gonna apply one hot encoding, and quant being the quantitative values. After segregating them, we need to do some basic EDS, so I'll just leave all these cells running as of now. Just a minute. Yes. So back over here, you guys might be confused about what label and one hot are. So basically, label encoding would be something, let's say if there are a column of three qualitative values, like over here you can see food name has three values: apple, chicken, and broccoli. So by label encoding, what we can do is that we can denote three numbers to represent these qualitative values, basically converting labels into numerical forms so that it's machine readable. So over here, as you can see, apple has been assigned 1, chicken with 2, and broccoli with 3. One hot encoding does the same thing, but unlike label encoding, there are three separate columns that will be created. Like you can see over here, apple, chicken, and broccoli has been separated into three separate columns, where 1 means true and 0 means false. Now, you see, you should use labels when the values are related, like let's say good, bad, or average. Even if your model is not entirely accurate, it might assume average instead of good, so that's an advantage. But you should use one hot encoding when the values are entirely distinct and should not be mixed. Like let's say for our dataset, it's going to be gender. Also, Label encoding should be used when the number of categories is quite high. Because one-hot encoding will lead to memory consumption. Because let's say if your dataset has like around 100 columns and each columns has got like 20 variations, so you cannot just have that many columns for one-hot encoding now. Alright, let's get back to the code. What we are going to do next is EDA, which is basically exploratory data analysis. So over here, if you notice in this graph, I have plotted how many predictions for our model is no and how many are yes. And it is to be noted that the number of yes is very less than the number of no. Okay, we'll get back to this later. Apart from that, we have just checked over here how the quantitative data is varying with respect to each other, like whether the data is scattered or whether it is bound to one specific point of the data set. Yes, in these 3 line plots we are passing the entire data set in long form mode. So this will aggregate over repeated values to show the mean and 95% confidence interval. Yeah, moving on, like I already explained, one-hot encoding and label encoding. After segregating the values up here into 3 categories, label, one-hot and quantitative, we have just applied one-hot encoding and label encoding to the qualitative values. Alright, moving on. Yeah, so this is a heat map. Now a heat map is a data visualization technique that shows magnitude of a phenomenon as colored in 2 dimensions. Over here, if you can see, we have passed df.core inside the heat map. So core basically stands for correlation. df.core returns correlation between all the columns. The plotting shows to what extent all the values are correlated to each other. Yeah, if you can see, if it's really dark, then it's in a negative correlation. And as the color becomes lighter, the correlation increases. Alright, moving on. Just a minute, I'll just leave these 3 cells running. Yeah, back over here, I had asked you guys to observe that the number of no's is quite higher than the number of yes. This is why we need to use something called SMOTE on our dataset. Now what is SMOTE? SMOTE basically stands for Synthetic Minority Oversampling Technique. Just a minute. Yes. So a problem with imbalanced classification is that there are too few examples of the minority class for a model to effectively learn the decision boundary. Now, one way to solve this problem is to oversample the examples in the minority class. For us, it's yes. This can be achieved by simply duplicating examples from the minority class in the dataset prior to fitting a model. This helps in balancing the class distribution. Now, SMOTE synthesis new minority instances between existing minority instances. It generates the virtual training records by linear interpolation for the minority class. As you can see, these synthetic training records are generated by randomly selecting one or more of the k nearest neighbor for each example in the minority class. After the oversampling process, the data is reconstructed and then several classification models can be applied to it for processing the data. Getting back to the code, As you can see, after applying smooth, the number of yes and the number of no's in the data set is now almost equal. Over here, we'll be splitting the data into training and test, with the test size being 0.2, which means that 80% of the data will be used for training the models and the 20% of it will be saved so that we can test how accurate our models are. Alright, moving on, we'll start off with logistic regression. Now, logistic regression estimates the probability of an event occurring, such as let's say vote or didn't vote, based on a given dataset of independent variables. Since the outcome is a probability, the dependent variable is bounded between 0 and 1. Now, many of you might wonder why we call it regression despite the fact that it's a classification algorithm. Now, logistic regression is termed as regression, but that is because it has the same mathematical formula as that of linear regression. Logistic regression calculates the log odds of an event happening, which is a continuous value. But on applying sigmoid function to it, we get discrete values, which are, for our case, 0 and 1. Now, you might be wondering what these are in the headings, ROC and confusion metrics. So basically, ROC curves in logistic regression are used for determining the best cutoff value for predicting whether a new observation is a failure, that is 0, or success, which will be 1. An ROC curve, also known as receiver operating characteristics curve, is a graph which shows the performance of a classification model at all classification thresholds. Like, just a minute. Yes, so the ROC curve has got two parameters: the true positive rate, which is pointed towards the y-axis, and the false positive rate, which is represented in the x-axis. Now, true positive rate is also a synonym for recall and is therefore defined as follows. As you can see, true positive rate will be equal to true positive whole divided by true positive plus false negative, and false positive rate would be false positive whole divided by false positive plus true negative. Now, you might be wondering what true positive, true negative, FP, FN, these are. So, for our case, we are predicting whether a person has got heart disease or not, right? So there are two categories. Let's say the two categories are, let's name them as patient and healthy. So patient will be those people who test positive for disease, and healthy will be those people who test negative for the disease. Alright. So true positive is basically the number of cases correctly identified as patient. False positive will be the number of cases incorrectly identified as patient. True negative will be the number of cases correctly identified as healthy, and false negative will be the number of cases incorrectly identified as healthy. Now, the accuracy of a test is its ability to differentiate the patient and the healthy cases correctly. Right. So, to estimate the accuracy of a test, we should calculate the proportion of true positive and true negative in all evaluated cases. So, mathematically, this can be stated as accuracy will be equal to summation of true positive and true negative whole divided by summation of true positive plus true negative plus F positive plus F negative. As you can also see in our data set, apart from logistic regression, we have something called a confusion matrix, We'll get back to the code in a minute. So what is a confusion matrix? A confusion matrix is basically a technique for summarizing the performance of a classification algorithm. Now, as you can see, as I have already mentioned earlier, that true positive are those predicted values which are positive and it's actually positive, right? You can check the same for false positive, false negative, and true negative. Now, in our data set, since we are trying to predict whether a person has heart disease or not, and since we already saw that the number of no's were way more than the number of yes, over here we'll have to make a note that for which classification algorithm the value of false positive and false negative is least. Alright, so getting back to the code, this is our logistic regression, which has an accuracy of around 85%, the ROC curve for it, and the confusion matrix. So as you can see, in the confusion matrix, we have something like 8,900 values of false negative and around 7,800 values of false positive. Moving on. Alright, so the next classification algorithm that we are going to try is the decision tree. Now, decision tree, it's an algorithm that uses a set of rules to make decisions, similarly to how humans make decisions. You know, every time you answer a question, you're also creating branches and segmenting the feature space into disjoint regions. So one branch of the tree has all data points corresponding to answering yes to the question, the rule in the previous node implied. The other branch has a node with the remaining data points. This way, you narrow down the feature space with each split or branch in the tree, and each data point will only belong to one region. Now, the goal is to continue splitting the feature space and applying rules until you don't have any more data points left. So as you can see over here, we started off the decision tree with the characteristics outlook. Alright, so now outlook is of three kinds: sunny, overcast, and rainy. And if you see, whenever it's overcast, the player can always play golf. So it's just an yes. But when it's sunny, we are again dividing the decision tree based on another choice. We are checking whether it's windy or not. If it's not windy, the prediction will be yes. If it's windy, then it's no. Similarly, on the rainy side, we are checking it in terms of humidity. You see, if it's outlook, like depending on the outlook, if it's rainy and if the humidity is normal, then the player can play golf. But if it's rainy and the humidity is high, then the player cannot play golf. This would be the ROC curve and the confusion matrix for decision trees. As you can see, compared to logistic regression, we have a lesser amount of false positive and false negative in the confusion matrix, which means that decision tree is giving us slightly better advantage over logistic regression. Moving on, we'll be checking for random forest classifier. Now, what is a random forest classifier? Random forest, like its name implies, consists of a large number of individual decision trees that operate as an ensemble. Each individual tree in the random forest spits out a class prediction, and the class with the most votes becomes our model's prediction. The fundamental concept behind random forest is simple but yet a very powerful one: the wisdom of crowds. A large number of relatively uncorrelated models operating as a committee will outperform any of the individual constituent models. The row correlation between the model is the key to the success of random forest. Now, decision trees are very sensitive to the data that they are trained on. A slight amount of change to the training set can result in significantly different tree structures. But random forest takes advantage of this by allowing each individual tree to randomly sample from the dataset with replacement, resulting in different trees. This process is known as packing. Now, in a normal decision tree, when it is time to split a node, we consider every possible feature and pick the one that produces the most separation between the observations in the left node versus those in the right node. In contrast, each tree in a random forest can pick only from a random subset of features. This forces even more variations among the trees in the model and ultimately results in low correlation across trees and more diversification. Alright, so moving on. The next classification algorithm in hand is XGBoost. Now, XGBoost, which stands for Extreme Gradient Boosting, is a scalable distributed gradient boosted decision tree machine learning library. It provides parallel tree boosting and is the leading machine learning library for both regression and classification. Just a minute, sorry for the interruption, but seems like I'm running low on power. Yeah, sorry. Now, as we already know, decision trees create a model that predicts the label by evaluating a tree of if then else, that is true or false feature questions, and then estimating the minimum number of questions needed to assess the probability of making a correct decision. A gradient boosting decision tree is a decision tree ensemble learning algorithm very similar to a random forest for classification and regression. Ensemble learning algorithms combine multiple machine learning algorithms to obtain a better model. The term gradient boosting comes from the idea of boosting or improving a single weak model by combining it with a number of other weak models in order to generate a collectively strong model. Gradient boosting is an extension of boosting, but the process of additively generating weak models is formalized as a gradient descent algorithm over an objective function. Gradient boosting sets target outcomes for the next model in an effort to minimize errors. Targeted outcomes for each case are based on the gradient of the error, hence the name gradient boosting, with respect to the prediction. Yes, as you can see, gradient boosting, XGBoost is actually performing quite well because number of false positives and false negatives are quite low given that true positives and true negatives are so high. I believe everyone has heard of Bayes theorem. That's what we're gonna try next. Just a minute. Yeah, the output was like quite fast. But let's get back to the theory of it first. So, this classification algorithm uses Bayes theorem to classify objects. The classifier assumes strong or naive independence between attributes of data points. This theorem states that conditional probability of an event based on the occurrence of another event is equal to the likelihood of the second event given the first event is multiplied by the probability of the first event. Okay, that sounded quite confusing, but let's have a look at this data set once. It's very similar to the one that we observed earlier. Over here we have various outlooks, which are rainy, sunny and overcast, and based on that we are seeing if a person can play a game or not. Now the formula of the theorem is this. So suppose we have a data set of weather conditions and corresponding target variable play. Using this data set, we need to decide whether we should play or not on a particular day according to the weather conditions. So to solve this, we actually need to convert the data set by following a few steps. First of all, we will convert the given data set into frequency tables. Then we will generate likelihood table by finding the probabilities of given features. Now using the theorem, we will calculate the posterior probability. Alright, so this is the frequency table for the weather condition, and this is the likelihood table for weather condition. Now if you see, if we apply the theorem to it, the formula would be probability of a player playing given the weather is sunny is equal to probability of the weather being sunny given the player is playing into probability of the player playing whole divided by probability of the weather being sunny. Now from the data observed, you can clearly understand that the probability of the weather being sunny given that the player is playing is 3 out of 10, which is 0.3. Similarly, probability of it being sunny would be 0.35. Probability of the player playing given that the weather is sunny will thereby be 0.3 into 0.71 divided by 0.35, which is 0.6. Similarly, you can calculate probability of the player not playing given the weather is sunny from the following table. And after applying the formulas, we can see probability of the player playing given the weather is sunny is more than the probability of the player not playing given the weather is sunny. Hence, on a sunny day, a player can play the game. Alright, moving on. Let's get back to the code. As you can see, doesn't seem like we are getting a very good output using this classification technique. So let's move on to our next one, which is SGD. Now SGD stands for Stochastic Gradient Descent. It is a simple and yet very efficient optimization algorithm and is used to find the values of parameters or coefficients of the functions that minimize a cost function. Just a minute, I'll let the cells running. Now, what is a cost function? So, cost functions are used to estimate how badly models are performing. To put it simply, a cost function is a measure of how wrong the model is in terms of its ability to estimate the relationship between x and y. This is typically expressed as a difference or distance between the predicted value and the actual value. What is gradient descent? So, gradient descent is an iterative first order optimization algorithm used to find a local minimum or maximum of a given function. Basically, in simple terms, a cost function is something that we want to minimize. For example, our cost function might be the sum of squared errors over the training set, and gradient descent is a method for finding the minimum of a function of these multiple variables. In here, the word stochastic means system or process linked with a random probability. Hence, SGD in SGT, a few samples are selected randomly instead of the whole data set for each iteration. This classifier basically implements a plain SGD learning routine supporting various loss functions and penalties for classification. You will learn more about SGD and other gradient descents in the upcoming part. I hope you enjoyed analyzing the dataset and learned something new.
Hey guys, my name is Sarthak and I will be talking about the gradient descent algorithm. The gradient descent method lays the foundation for machine learning and deep learning techniques. Let's explore how it works, when to use it, and how it behaves for various functions. Gradient descent is an iterative first order optimization algorithm used to find a local minimum or maximum of a given function. Think of it this way. Imagine standing on top of some hilly terrain, blindfolded, and being required to get as low as possible. It shouldn't strike you as a necessarily difficult problem. You'd probably just try to figure out which way is downhill and head that way. Just keep going down until you can't go down anymore. That's gradient descent. This algorithm is not exactly rocket science. First, figure out which way is downhill, then take a few steps, and repeat the same process. This method is commonly used in machine learning and deep learning to minimize a cost. However, it is not limited to machine learning or deep learning only. It is being widely used also in areas like robotics, video games, software, and mechanical engineering. That's why today we will get a deep dive into the math, implementation, and behavior of first order gradient descent algorithm. First, we use the make regression function of the scikit-learn library to produce a data set with 1000 samples and only one feature. The data will be continuous in nature, making it a regression problem. A regression problem is when the output variable is real or continuous value, such as salary or weight. Many different models can be used. The simplest is the linear regression. It tries to fit data with the best hyperplane which goes through the points. First, we must decide how we're going to represent functions or hypothesis h in a computer. As an initial choice, let's say we decide to approximate y as a linear function of x. Here, the thetas are the parameters, also called weights, parameterizing the space of linear functions mapping from x to y. Now, given a training set, how do we pick or learn the parameters theta? One reasonable method seems to be to make the prediction close to the actual value, at least for the four training examples that we have. To formalize this, we will define a function that measures for each value of the parameters how close the actual values are to the corresponding predicted values. We define the cost function, which is actually the predicted value minus the actual value, summed over all the training examples. We want to choose theta so as to minimize the cost. To do so, let's use a search algorithm that starts with some initial guess for theta and that repeatedly changes theta to make the cost smaller until we converge to a value of theta that minimizes the cost. Specifically, let's consider the gradient descent algorithm, which starts with some initial parameters and repeatedly performs this update. Here, alpha is the learning rate. This is a very natural algorithm that repeatedly takes a step in the direction of steepest decrease of the cost. Now, let's try to work out the partial derivative term on the right. After derivating, this is what the rule becomes. This rule has several properties that seem natural and intuitive. For instance, the magnitude of the update is proportional to the error term. Thus, for instance, if we are encountering a training example on which our prediction nearly matches the actual value, then we find that there is little need to change the parameters. In contrast, a larger change to the parameters will be made if our prediction has a large error. There are two ways to modify this method for a training set of more than one example. The first is to replace it with the following algorithm. This is simply gradient descent on the original cost function. This method looks at every example in the entire training set on every step and is called batch gradient descent. Gradient descent can be vulnerable to local minima in general, but the optimization problem we have posted here for linear regression has only one global and no other local optima. Thus, gradient descent always converges to the global minimum. Here, the cost is a quadratic function. The ellipses shown above are contours of a quadratic function. Also shown is a trajectory taken by gradient descent. The x's in the figure mark the successive values of parameters that gradient descent went through. So now we will go through the implementation of this algorithm in Python. The only external library we will be using is NumPy, which has support for large multi-directional arrays and matrices, which we often encounter in machine learning. First, we perform linear regression using inbuilt methods from the SciPy library. This is the slope and these are the values of the intercept and the slope that we get. When we plot these values, this is the line which goes through the data. So now we will go through the implementation of this algorithm from scratch. This is the cost function which implements the formula that we saw earlier. And this is the implementation of batch gradient descent. We use a learning rate alpha with value 0.05. The number of iterations we will go through is 1000. After running the algorithm, we see that the intercept and the slope that we get are same as we got through linear regression with SciPy. This algorithm is very fast and has execute and went through 1000 iterations in 42 milliseconds only. But the final cost is very high, meaning it is computationally very expensive. When we plot the cost with respect to each iteration, we see that we converge to the minimum on the 50th iteration itself. Thus, 1000 iterations were not needed. Next, we move on to stochastic gradient descent. In this algorithm, we repeatedly run through the training set, and each time we encounter a training example, we update the parameters according to the gradient of the error with respect to that single training example only. This algorithm is called stochastic gradient descent. Whereas batch gradient descent has to scan through the entire training set before taking a single step, which is a costly operation if M is large, stochastic gradient descent can start making progress right away and continues to make progress with each example it looks at. Now, let's learn the importance of learning rate, alpha. The learning rate controls the size of each step taken by gradient descent. For gradient descent to work correctly, you need to take small steps in between assessing the situation and potentially changing direction. The size of the steps you take need to be small relative to the speed with which the terrain is moving. Put another way, effective gradient descent should involve constantly checking the lay of the land and figuring out which way downhill is. If you aren't checking often enough, you will wander aimlessly. The lesson here is quite simple. Frequent feedback is good. Any real life procedure that involves iterating rapidly is often a form of gradient descent. If the learning rate is too large, the gradient descent might miss the global minimum. If the learning rate is too small, then the algorithm will take too long to converge. Here is the implementation of stochastic gradient descent algorithm. We use random indexes instead of going through the training example sequentially, which makes our algorithm more efficient. This time we use a learning rate of 0.05 and we will go through 1000 iterations. We got the correct answer and the final cost is much lower than that of batch gradient descent, but the algorithm took 31 seconds to run, which is very slow. Often, stochastic gradient descent gets the parameters close to the minimum much faster than batch gradient descent, but it may never converge to the minimum, and the parameters will keep oscillating around the minimum of the cost. But in practice, most of the values near the minimum will be reasonably good approximations to the true minimum. For these reasons, particularly when the training set is large, stochastic gradient descent is often preferred over batch gradient descent. Here is the plot of cost with respect to each iteration. Next, we move on to mini batch gradient descent. Batch gradient descent can be used for smoother curves and converges directly to the minima, but is computationally very expensive for large datasets. Stochastic gradient descent converges faster and can be used when dataset is large, but since in stochastic gradient descent we only use one example at a time, we cannot implement the vectorized implementation on it. This can slow down the computations. To tackle this problem, a mixture of batch gradient descent and stochastic gradient descent is used. Neither we use all the dataset all at once, nor we use the single example at a time. We use a batch of fixed number of training examples, which is less than the actual dataset, and call it a mini batch. Doing this helps us achieve the advantages of both the former variants that we saw. So, after creating one mini batch of fixed size, we do the following steps in one epoch. We pick a mini batch, we calculate the mean gradient of the mini batch, then we use the mean gradient we calculated to update the weights. Then we repeat these steps for all the mini batches that we created. This is the implementation. We use random indexes again and then create our batches of size 20. Then we update the parameters and move forward to the next batch. We use the same learning rate and go through 1000 iterations. We observe that the algorithm executed in 3 seconds, but which is neither too large nor too small. Even the cost is in between that of batch gradient descent and stochastic gradient descent. It is the best of both worlds. As we can see, the cost converged to the minimum in 50 iterations itself. Like everything, all three types of gradient descent algorithms have their advantages as well as their Like everything, all the three types of gradient descent algorithms have their advantages as well as disadvantages. It's not like one variant is used frequently over all the others. Every variant is used uniformly depending on the situation and context of the problem. This will be a good starting point for you to explore more advanced gradient based optimization methods like momentum or Nesterov gradient descent, RMS prop, Adam, or second order ones like the Newton Raphson algorithm. That's it from my side. Thank you all for watching our session.